So hello everyone and welcome to the Quantum Monte Carlo workshop. My name is Paul Kent. I'm staff at Oak Ridge National Lab and I'm one of the organizers. We've really been looking forward to getting started with this workshop. It's great to see so many people here and we're really looking forward to going through Quantum Monte Carlo over the next 8 weeks. You can actually follow along these slides on this GitHub link, and that's actually also where we will be having all the example files that we'll be following throughout the workshop. Today, this is basically going to be a short introduction and kickoff going through some of the logistics, and then we're going to get fully up to speed in the following weeks. Before going further, I want to acknowledge our funders, the US Department of Energy Office of Science, through their Computational Materials Sciences program and the center that I direct. And you can see the 5 different institutions that are involved there at the bottom. So let me give a warm welcome to everyone. We actually have over 200 registrants for this workshop from really around the globe. And I can see there's already over 100 people on the Slack that we've set up on the workshop. So welcome, and it's great to see all this interest. A few people have emailed to say that they're going to be bravely joining from a very inconvenient time zones. So that's really appreciated. Welcome to actually help with this. We are going to be recording these presentations and we're going to try and upload them fairly promptly after the live presentations so that you can follow along in the same weeks. And indeed, even if you're able to enjoy the presentations live, you'll be able to go back and rewatch if needed. Of course, it's been a while since we've done any sort of in-person workshop, and it's great to see so many people interested in this virtual form. So what are we going to cover today? Well, it's really quite a simple setup. I'm going to spend a little bit of time motivating why we might be interested in Quantum Monte Carlo. And then I'm going to spend most of the time going through the logistics for this virtual workshop and also covering using the VirtualBox virtual machine image that we've produced. For anyone who's joined other virtual workshops, the setup is probably going to be very familiar to you, but we've got to assume there may be a few people for whom this is completely new. And then we will have a little bit of time if there are any questions at the end, although I think there'll be much more interactivity in the following weeks. And indeed, next week, we're going to be covering the theory of real space quantum Monte Carlo in broad brushstrokes. And I think, unlike today, which is going to be shorter, we're going to be using the full 2-hour slot to go over that. So some notes on the practicalities. As I've mentioned, we're recording these for upload to YouTube, so bear that in mind. And one thing I really want to stress, one thing that makes these workshops most successful is questions and interactivity. And we've got at least 2 ways of doing that. There's the chat feature in Zoom, and also we have the workshop Slack. We've also got the ability to unmute people, so indicate if you wish to ask a question live. Now, what is the difference between these 2 routes? Well, if you ask a question in the Zoom, after the live presentation, it becomes very hard to access those. Whereas anything on Slack is going to remain accessible long term. So a deeper question there might be better suited to a Slack. And of course, we have a chance to follow up with everybody on Slack a bit more easily. And just to ensure that actually the presenters don't get too focused on their material and miss questions, each week we've got someone keeping an eye on both of these. So thanks to my colleague Anna Banali at Argonne, who's keeping an eye on both of these today. So some additional important acknowledgements. It takes quite a bit of effort, a lot of time to put together these presentations and all the example files. I don't have current pictures of everyone who's presenting, so let me just read their names. So my thanks in particular to Chandler Bennett and Jaron Krogel at Oak Ridge, Anna Banali at Argonne, Cody Melton and Joshua Townsend at Sandia Labs, and Gani Anabediev and Lubosh Mitesh at North Carolina State University. And I'd also like to acknowledge the help at Oak Ridge of Laura Becker, who put together our website and registration system, and Makisha Mitchell for admin help. And really, of course, we're building on the efforts and contributions of all the current QMC Pack developers and users, thanks to them. So let me point out some goals for the workshop. So this is how you see if you're in the right place. What we aim to do is cover the fundamentals of quantum Monte Carlo. And then we're going to be providing a foundation for practical molecular or chemical calculations, and also solid state or periodic calculations using the QMC Pack Quantum Monte Carlo code. And we're going to be obtaining trial wave functions from either Pi SCF or Quantum Espresso. We're, of course, interfaced to other applications such as the real space multigrid DFT code and games, but these are what we're focusing on in this workshop. We're going to hear about some relatively recent developments, such as the theoretical background and implementation of the spin-orbit interaction into quantum Monte Carlo, which of course opens up lots of chemistry and physics, and also hearing about some recent research. And then importantly, we're not going to disappear after the workshop. Inevitably, there's going to be more questions when one tries to set up real-world research problems. So we're going to give some indications for how to contact us, maintaining contact after the workshop. So that's very welcome. Thanks to everyone who put suggestions in the survey we had on registration. These above topics were actually what was most requested. Of course, there were more topics that we wanted to include ourselves, and a few more requested, but we've only got 8 weeks. So there's only a certain amount of time. However, given the interest in this workshop, and of course, learning about the power of virtual workshops, I think it's extremely likely that we're going to do another one next year, perhaps late spring, early summer. And so when we send out a survey at the end of this workshop, please put in there anything that you would like to see or topic recapped. Thanks. So some notes on the scheduling. I see there's a lot of us here, so that seems to work out, but we will be at the same time each week. So Tuesdays at 11 o'clock Eastern time for up to 2 hours. And the format is going to be essentially a presentation, and then going through some worked examples, which we've made the files available. And then the idea is that after the presentation, you can go through these and run them yourselves directly, and then of course then make your own experimentations and variations during the week. So I think in a few weeks we're going to be learning about running the water molecule, and obviously having done that, you could think to switch it for methane or ethanol or benzene, whatever your favorite small molecule is. We'll be providing out of hours support via Slack. So this is one of the reasons why it's helpful to register there if you're able. And I hope not to jinx ourselves or even jinx this current talk by mentioning this right now, but if we have some technical issues, we're going to try to reschedule the same week so that we can stick to the same overall 8-week schedule. So perhaps on the Wednesday or Thursday, although fingers crossed that doesn't happen. And one thing I realized when I was writing down the schedule, of course, is that clocks change around the end of October and November. So that's something to bear in mind. So in the USA, this happens on the 7th of November. And I know in Europe, it's a week earlier. So around that time, be careful. We'll be starting at 11 o'clock Eastern, whatever that happens to be, where you are. So let me walk through the schedule. This is also up on the website. So as I've mentioned, next week, we're going to be covering the theory and fundamentals of quantum Monte Carlo. And then over the weeks that follow, we're going to be covering the various jigsaw puzzle pieces that need to come together to do an efficient quantum Monte Carlo calculation, and then importantly, learn something scientific from it. So since we're going to be running multiple codes, one thing that's very efficient to use is computational workflows. We have some software called Nexus for that. That'll be presented by Jaron Krogel. And then also, of course, an important distinction between quantum Monte Carlo methods and, for example, coupled cluster is that quantum Monte Carlo is a statistical method. It's a Monte Carlo method, so of course we have to do statistical analysis, and we'll also cover that. And over the following weeks, molecular and periodic calculations. And then in week 6, we'll be learning about the key considerations and actually some of the recent developments for using shooter potentials in quantum Monte Carlo. One doesn't have to use them, of course, but of course, in general, like with any method, if you can avoid paying for the core electrons, if they don't contribute to the properties in your system very much, we don't want to pay for them. Then we'll also hear about observables, which is our code name for properties such as the charge density and other such properties that we need to analyze to understand more about the system than just what the energy tells us. Week 7 will be a change of pace. We're going to have some guest lectures and research presentations. And our first speaker is going to be Claudia Philippi from the University of Twente in the Netherlands. And then finally, in our last week, we'll be hearing about spin orbit calculations on molecular systems. And then we'll have a wrap up and discuss next steps. So I'm really looking forward to the next 8 weeks. Just some logistics here. I know over 100 people are on Slack already, so I think people are able to use the link, and that's working. Obviously, we want to use this to discuss, provide any needed support, answer any questions. There's various channels set up, and of course, we can make new ones if that turns out to be pertinent. This will help the workshop be interactive. And for anyone who's relatively new to using Slack, you can control the notifications that it gives you, so you can, of course, switch off the interruptions if you find them to be annoying, or maybe even leave them all enabled if you wish. What about then after the workshop? Well, we're not going to close that channel immediately. We'll keep that open for some months, just keep an eye on the usage. But then the two main routes to get support afterwards are here. So we have an open group on Google where you can put really general science questions, more methodological questions. And you see it's a fairly low traffic list. There's a couple of messages per month typically. And then perhaps for something more technical, you can certainly put science questions here as well. You can put a note, make an issue on the QMC Pack GitHub page. And of course, we track every reported issue on the code and its use there as well. You can, of course, contact people directly, but I'd really encourage everyone to use these two routes, the Google group or GitHub. And that's because more people will be able to participate in the conversation. And of course, then the questions and answers become visible through search. So hopefully other people will then also benefit. All right, so why quantum Monte Carlo? This could, of course, be a whole lecture series, but I put together a half-dozen slides here to cover some of the main features and motivations. But first, actually, what I want to do is actually take a step back, right? We are in a really exciting time in the history of electronic structure methods and quantum chemistry. They're incredibly impactful. And of course, they're now routinely a part of experimental papers directly contributing to either identifying new systems or understanding them, working out how they can be improved. And I've shown a couple of examples here, just for brevity. These are in the materials space. We could do the same thing in chemistry as well and spend many slides going through these. So first here on the left, I've got an example of a prediction of a relative exotic property. We probably all saw the news last year of the claim of experimental measurement of room temperature superconductivity. although of course, unfortunately not at room pressures. This is a high pressure experiment. And this was in the hydrogen sulfide system. And of course, that work traces back to high throughput calculations looking at the phase diagram in the hydrogen sulfide system. So if other groups can reproduce these results, that will be a very big success. And of course, in other areas, we know that you can use a cheap enough method that you can use you can compute a large number of results. So one famous example of this comes from Professor Gert Seder's group. This is already in 2010. And this shows the predicted voltage and capacity for a whole range of different battery cathodes. So all of these dots is a new material. And of course, one can use this to understand trends, perhaps guide synthesis. And of course, these days we talk about, of course, this work has led into things like the materials project, computational databases. And of course, these days we might also think about AI and machine learning, training potentials, these sorts of things. So what's the relevance of this? Well, if we look at really any modern publication, we see that all the computational research is using a range of methods, and they've all got their own strengths and weaknesses. And so we need to choose appropriately for the task at hand. So for example, there's been an uptick in the use of tight binding because of the twisted graphene and a work on topological materials. Of course, you have to have the right Hamiltonian and the parameters for the Hamiltonian there. GW is, of course, a really excellent method for optical properties of materials, but we relatively rarely use it to find out the location of atoms in materials. So it's not used as a total energy method. Let me pick on couple cluster singles doubles with perturbative triples. So this is really the gold standard quantum chemical method. We know that it has, of course, a high power scaling with system size. It's a basis set method. And of course, as a system has multi-reference character, it starts to break down. And that's really a topic of ongoing research. And of course, similarly, there are issues, as we all know, with different density functional approximations. How does one pick, particularly if you don't have any, you're trying to predict a new material. So then what are the interesting and important points about quantum Monte Carlo? So here I've got 4 key features. And this is sort of my view. I'm sure other presenters will include some of their own views in their own presentation in the following weeks. And I've got a slide of each of these. So first, and I think this is actually probably why most of us are here and perhaps why many of us got into using the methods. They're really very, very accurate in their simplest form. So this makes them very useful for benchmarking, providing reference data on material and chemical systems when other methods might be in question. But then there's some other points which I think are going to take increasing relevance over the coming years. One of the interesting things about quantum Monte Carlo methods is that there are not very many approximations in them. And actually what those approximations are is known. And it's increasingly possible to reduce the errors that result from those approximations and converge the results. So one can envisage a time in the near future when we can start to say what the uncertainty in our predictions is. And this is the kind of thing I want to be able to tell to my experimental colleagues down the corridor, right? If we predict a new material, how much confidence do we have in the predicted properties? If they're initially unsuccessful in synthesizing the material, should they try really hard because we're very confident in the property? Or should they stop at that point and save their time and work on another material? Thirdly, these are, of course, full many-body quantum mechanical methods. So in principle, we have the wave function and we can access lots of many-body physics. And then finally, as I touch on, the methods are increasingly affordable, not just because of the increase in computational power, which of course has been immense over the years, but also the methods and algorithms are getting much better. So let's walk through these now. So first, let's talk about the accuracy of the sort of standard recipes as we'll be covering in this workshop. Why might they be accurate? Well, one of the reasons behind this is that the methods avoid some of the mistakes that cheaper, more approximate methods tend to make. So for example, at least in a finite system, electrons don't interact with themselves, and we don't have double counting or self-interaction errors, and that helps immensely. And it also turns out that things like the van der Waals interaction get naturally included relatively straightforwardly. And so that's a big help, a big step up over other cheaper approaches. So just to show some examples of this, here on the left, these are some results for a fairly simple material. So scandium oxide, this work was done by Keohane and Saritas a few years ago. And I'm showing this, so these are the results for different polymorphs. And I'm showing this because this is an example where we actually have experimental results, so experimental calorimetry for several different phases. And of course, this is something that we may not have for a new material or a 2D nanostructure, for example. So we're very fortunate to have calorimetry here. And we see that the diffusion Monte Carlo results actually match up within error bars very nicely in this case. And then often what one is trying to do is use this to inform the selection of an approximate density functional, which one can then use on maybe more complex systems or just more extensively. And this was a case where, at least in this paper, of the functionals tried, unfortunately, none of them matched either the experimental trend or the quantum Monte Carlo trend, right? So this is an area where you would need to use quantum Monte Carlo. On the topic of van der Waals interactions, so graphite stacking was looked at by Leonardo Spano in Giulio Galli's group some years back. And sort of the most accurate result is sort of around this point here. And we see that it has a good match with the experimental lattice constant and also the binding energy. And there's been follow-on calculations since. And then finally, there've actually been a very large number of molecular calculations performed looking at van der Waals binding. So this, of course, shows benzene stacking, which is a famous test case. And for anyone interested in this, I draw your attention. There's a very nice extensive review paper by Metastubexi in Chemical Reviews. And in addition to going through a variety of molecular applications, it also has a very nice introduction to quantum Monte Carlo methods as well. So that would actually help in this workshop. So the next point is about the approvability of these methods. Now, of course, it's worth stating that quantum Monte Carlo methods are not magically accurate. There are things that need to be done to make these improvements. And actually here I'm going to show a result of actually doing that. This is from Michel Caffarel and his group, looking at the water molecule. And so here we have energy, and the methods are actually variational in the energy as run here. So we know formally that lower is better. That's a nice feature of the methods. And here we see the results from the diffusion Monte Carlo, and this is basis set size, so it's convergence moving to the left, and that's done and extrapolated. And I think this might still be the most accurate calculation of the water molecule that's been done. So we see an agreement to lots of digits with the experimental formation enthalpy. And so this is done by, as we may hear a little bit about this, by systematic improvements of the trial wave function. So this is something that's starting to become possible, actually not just for water, but for increasingly large systems over time. Just to touch back on the magic, of course, there are technical parameters that we have to take care to converge as well, as we'll be hearing, things like the time step. And in periodic calculations, one has to do large enough supercells and so on, as well as in other many-body methods. And now something that's sort of dear to my heart and certainly a little bit underexploited in the field, in my opinion. These are, of course, full many-body methods. So we can get to quantities, at least in principle, that one couldn't get to in a single particle or mean field method, right? So the wave function is potentially accessible. So any property that we can write down the correct operator for working on the wave function can in principle be computed. So there are lots of interesting properties to do with how electrons move in the material, how they respond, that could be looked at. Here's two examples in that direction. So first, this is the pair correlation function around an electron in silicon. And so what we're doing here, we're sitting in the middle of a bond, 110 bond, and this plot shows essentially how far we have to go till we meet another electron. And we can see there's some structure to this. And this is something that we can presumably learn a lot about the correlations and properties of material. And I think this has only been done in silicon and in a variety of atoms and the homogeneous electron on gas and variations of it. So there's a lot of materials which have interesting physics where this could also be looked at. We can also look at properties such as the momentum distribution. This shows that some of the differences in the momentum distribution in vanadia going through a phase transition. And in addition to producing visually striking results that we can interpret, here the consequences are that one can connect through to things like Compton scattering, and so we get another experimental connection through that. And of course, there's a lot more that could be done, even actually on relatively small systems that could be run relatively cheaply. And on that topic, I think it's important that we address computational costs. As with any methods, it's certainly possible to write down a very expensive calculation. And of course, we're going to be giving guidance about how to make sure you only do that intentionally. And I think I'm going to date myself here for how long I've been working on quantum Monte Carlo. So this result actually is from my PhD. And, then I went off and did other methods and came back recently when I realized actually we really do need quantum Monte Carlo for current research. Back then, I was looking at how large a carbon cluster do you need to start seeing stable fullerenes? When does that transition to the cage structure happen? And I seem to remember it was around C26 or so. And this is a case where actually even today you can get all sorts of different results with less accurate methods. Also around the same time, some of the first defect calculations were done. And of course, defect properties in materials are very important and another area where we may want to have the additional accuracy or validation on other methods. And I remember actually back running this, I got into a little bit of trouble because I used a large fraction of our group's computing time. And fortunately, it worked out and we got good results. But looking back at that today, how expensive was that calculation? And how expensive would it be to run it today? So here on the right, this is the top 500 list of the fastest 500 publicly declared supercomputers. So higher performance is vertical, and this is year going across. Number one is these triangles, and number 500 is this bottom line. And back then, these calculations weren't being done on the top one machine. They were on a strong supercomputer, but so somewhere down around here. So we are now many orders of magnitude higher all those years later. And if we look at the performance of a workstation, or at least if we could find them to buy them, a graphical processing unit, GPU card, that's just around here, right, on the machine that we could have under our desk, or certainly with departmental resources, which would of course be higher. And I mention this because the cost of the calculation comes from the physics, the elemental types, and the electron count. So if we were to run, for example, boron nitride instead of the carbons, right, we would expect somewhat similar cost. And so this sort of work, looking at some new nanostructures, for example, would be a very straightforward thing to do today. So hopefully that's enough initial motivation. We'll be hearing more over the following weeks. And so now I want to really change the topic to something that's more practical, which is how to use the workshop virtual machine that we've prepared. So what is this virtual machine? So what it is, it's a Ubuntu desktop that has got a variety of electronic structure software installed, as well as the quantum Monte Carlo software. And so one can run calculations on there directly without having to install the software yourself. So it's got QMC Pack, the workflow software Nexus, Quantum Espresso, PySCF, the Dirac relativistic quantum chemistry code, and for visualization, Vesta and XChristN and the workshop files. Now, VirtualBox runs on x86 architectures, so that's what we can support. And the problems are size, so that if you have a reasonably recent or a strong laptop, you should be able to run. Some may take some tens of minutes and won't be instant, but should still have fast enough turnover. I'm going to give some workarounds and alternatives in a few slides for if perhaps you have a weaker laptop or a different architecture. We've got a few weeks for people to try this out. It's only really week 3, so in 2 weeks' time that we need this to work really well. But obviously, the earlier people try this, the sooner we'll be able to provide any help or suggestions if things are needed to get them working. And we'd actually really appreciate feedback on this. It's the first time we've put this to all these different codes together in a virtual machine image. And one of the things we actually had requested from previous workshops was to make a sort of a live image or virtual machine like this. And so we're doing that now, and would like to do that going forward. So if you can see a way of making improvements, please let us know. So how to use the image. So this slide is designed to be read. I'm not going to read it all out. You need to install VirtualBox. You need to download the file. Now, the workshop image file. Now, some notes about that. It's quite a large file, as is typical for that. So, choose your network wisely and perhaps retry if you have some issues. It takes 5 minutes to download here, for example. And then once you've done that, this will be completely standard to anyone who's used these before. You need to import the appliance and set up the machine image on your machine. And the main thing to really watch out for, and I'll show you this in a moment, is that you can tweak the settings when you import the image. So for example, if you're running on a more powerful machine, you might want to increase the core count or the amount of memory that it can use. And if you set 1 by accident, or maybe perhaps that's the default, things are going to be very slow. So let me just show that. Hopefully, there we go. So this is what it looks like running on a Mac. I've got a few-year-old Mac laptop. So I go to File, Import. I have to remember where I put the downloaded image. Just select the image, hit Open, hit Continue. And then the main thing to check here is that the CPU count and the memory usage is appropriate. So then we hit Import, and this will take a few minutes. So let's not wait for all of that. So then use of this should be fairly straightforward for anyone who's used the Ubuntu desktop or other sort of Linux type desktop fairly recently. One thing to note here, if you lock the screen or need to type sudo to install some software, the password is workshop21 with no quotes. You can sort of click down here for anyone who's not familiar with these to get to applications, one terminal or anything you like. In the terminal, the various codes are available on the path. So this should be fairly straightforward, and let us know how you get on. Let me just show everyone what that looks like. So here I've got the image. I make sure I select the right one. I hit Start. And on my machine, with everything I had running that time, it takes about 20 seconds or so to start up. So we're going to watch Ubuntu boot, and we'll eventually get to a terminal. Just watch this run. All right, you can of course resize the window. So here we have a terminal, and we can, for example, run QMC Pack, which will complain that I didn't give it an input file. And we can run Quantum Espresso, which will wait for input if we don't give it anything. And of course, this is a regular Linux desktop, so you can run a web browser if you need. Just be careful not to leave things running unnecessarily, because of course that will sap performance. So close things when you're not using them. So hopefully that's straightforward. And I think that's going to be a very productive way of going through the different workshop examples. So here's just a couple of alternatives. I have to stress that the main route that we're able to support is the sort of x86 VirtualBox route, but we'll try to help out as we're able if that route isn't open to you. So one alternative would be to run VirtualBox on a remote machine if you have a reasonable network to that machine. Of course, you need root to install VirtualBox. And this could actually be much, much better than running on a laptop, for example, because if it's a recent research workstation, you could get results much more quickly and do systems that are larger and more closer to those that one would publish on these days. So that could be really advantageous if that route is open for you. The other option would, of course, be to install the software directly. Now, if you look on our GitHub site, in the workshop image directory, the script that is used to create the image is there. There's also a README file about using the image and actually how we make the image. So it should be, if you're familiar with installing electronic structure software, this should be really straightforward to update. So for example, if you have a different Unix, switch out the package manager and so on. We're only using standard packages apart from the electronic structure software, of course. So this should be straightforward to update. And if you're not familiar with this, track down your local friendly neighborhood system administrator, and they should be able to make short work of this. Just some other things that we've tried to see other routes. If you can get to, if you're on an ARM machine and you can get to an Ubuntu on ARM, the script does indeed work there. And I'd like to thank Mark Doing at Argonne, who actually tried this out in WSL2 on Windows. And all the console parts work at least, but you'll be on your own as regards graphical support. That's out of the scope of what we can support. But there should be various different ways to get this all up to speed. So let us know in the chat on the Slack if you have questions about that. Now, one important step that we will all need to do each week, and that's just the reality of putting these together, is that there will be updates to the workshop files, and of course slides will be uploaded. So the workshop files are of course a Git repository, so you can CD into there and just do a Git pull, and if you do that each week, you'll get the updated files. If we have to make some updates to the Python, and I think we are going to have to do at least one of these, you can CD as shown here and also do a Git pull, and we'll send out instructions as needed. We are absolutely going to try to minimize anyone needing to re-download the workshop image, as we know it's quite a big download and inconvenient. We are going to try and get some new spin orbit capabilities in for the last week. So that's the one update we know about right now, but I think people will enjoy those new capabilities for very accurate quantum chemical applications. So that's how to update the files. Now, before I wrap up here, this sort of simple first week, some things to do if you haven't already. Register on Slack if you're able. And then sometime over the following days, get up to speed with VirtualBox, which you can store from the website, or some package manager for your system, and then download and get set up with the workshop image. So this has been a fairly straightforward presentation. I don't know if there will be any additional questions that haven't been covered so far. While I'm waiting for people to type, thanks everyone for joining, and I look forward to seeing everyone next week when we go through the full theory of real space quantum Monte Carlo. So let me see if there are any questions.
Hey, Paul, can you hear me? I think.
All right, I don't hear Anwar, but I can see some questions in the chat that have been asked. So for larger calculations, does QMC pack support GPU use? Absolutely, yes, it does. That's a little bit beyond the scope of what we can cover in this workshop, but that's really a major focus as an increasing number of GPU machines are coming online. So for example, in the US, the Perlmutter machine at NERSC is just being stood up. And of course, we want to be ready and hope we are ready on day one of all those machines. I see there's another question about using VASP. This will be covered over the following weeks. So the issue there is that we use the semi-local form of shooter potentials. So it's important to have a code where one can feed in appropriately accurate and tested shooter potentials. And so that's why we interface to codes such as Quantum Espresso or the real space multi-grid code, as we're able to do that. I see another question. Is there any work combining with ASC? And there are actually connections through Nexus. And I think that might be touched on in 2 weeks' time. So you can import structures through there. All right, let me just scroll up to see if there's any questions that I've missed. Thank you for providing answers as we went through. All right, thanks everyone for joining. Please, interact through the Slack over the next week, and I look forward to seeing everyone next week.